That's it. Someone said, I want to know since if I wear white shoes, I want to make sure I made it. Don't wear white shoes.
Oh, I already typed it out.
Alright, hey, take a seat. Take a seat. Alright, now, who in here still needs to finish that test at some point? Raise your hand. At least, alright, at least 4. Okay. So at some point during the study hall, before school, after school, sometime you need to make sure that you're getting in here to get that done. Okay? If we have a little bit of time at the end of class today, like once we're through some of these notes, because we're only going to take a few notes today, you can work on it in class. But that's at the end. No, we just got done with that. So just give me some basic intro notes today. But if we get done early, I have no idea how long it's going to take me. If we get done early, then those 4 can kind of work. Okay? Make sense? Okay, I want to get those tests tried to wrap up by tomorrow. So that's my goal. I want them done by tomorrow. Now, to give you kind of a heads up this week, today notes, tomorrow kind of we'll wrap up the section that we're in. So we might have a session tomorrow on this because it won't be big. It'll be actually quite small because there's not very much stuff. You'll see it once they do a few examples of it today.
You're small or are small?
You're small.
Okay.
So there's not much I can do.
Okay.
And then eventually this week we'll get into the later sections, which get a little more challenging. We're graphing quadratics and all this stuff. That's kind of where we're moving towards. Thursday this week, I'm not here. I'm gone. I'm going to the volleyball team on Thursday. So you have to sub. I'm going to try to work it out where it's kind of a work day. Where you just kind of stuff, get wrap up stuff. I don't like to give a lot of homework and stuff on the days I'm gone, but it'll be kind of a wrap up day where you kind of work on stuff. So just kind of keep that in mind. That'll be Thursday this week. Okay. All right. Let's try to finish up some of this stuff here, or like at least intro what I want to get through today. I want to talk about the rational numbers today. Rational, and that's kind of what we're in. We're in rational and polynomial equations. So I want to kind of talk about what we're discussing, what this concept is, why we're going into it, why we follow up chapter 1 which was all linear stuff with this stuff. Well, let's talk about the real numbers to begin with. And this is a chart that we had at the very beginning of the year. And it's a little chart we have, real numbers. Okay, in elementary school, we always start with a certain category of numbers that we learn about, right? The first category of numbers that you start with the capital N. Anyone know what those are called? Naturals. Okay? Those are the ones that we started in elementary with. Natural numbers, the symbol for natural numbers in college, it's an N, but it has like a secondary tail in it. Kind of like, let me draw it really big here so you can see this. Like that. That's the symbol they use. Natural numbers are 1 and up. And what they start teaching you is, how to add, subtract, multiply, and divide. Right? We get to some simple, basic arithmetic with that. The order of operations come into play. Then they branch out and they get to this next category, which is really not an actual category. It's just one that we throw in there because we add some more properties. And it starts with a W, or whole numbers. How I remember whole numbers, the O in whole, O, right? That's your first number that you're going to have, so 0. Right? O represents 0, and it goes up. So it's just a larger set of numbers, right? This natural number is a subset, smaller set of this group. This is the bigger group, because if we add one more number in there, right? So add 0. There's no symbol for the whole numbers. We just use a W. They don't have a symbol because they don't actually consider it an actual category of numbers in college. The next group that that they work with, usually about 4th grade, 3rd grade, 5th grade, somewhere in that range. Starts with an I. Integers. Now, the actual symbol that they use in college for integers is a Z. It's the symbol. It's the Z with the second tail. That's the actual symbol for it. It's any negative number and positive numbers. So it's kind of like the whole numbers, but we add their opposites as well. So this is a set, this is a subset, and this is another subset of the previous one. So we're starting to get bigger and bigger, right? And what we did in this last chapter, right, when we were talking about linear equations, we got to this next category, which was called rationals. The rational numbers is this outside category. Okay. The rational numbers, I believe in college they use a Q with an extra line in it, which I always find that really weird, because it has nothing to do with the rational, but this Q must be a Latin thing. But the rational numbers are anything you could write as a fraction. Anything. So any number you can write as a fraction, that's a rational number. And that's what we did all last chapter, if you think about it. We were doing slope and there's fractions. It was perfect. So that's kind of what we went into. Things that can also write as fractions, we can write decimals as fractions, certain decimals, right? Decimals that either repeating decimals, or they terminate at the end. So those are the types of decimals that you can write as fractions. Decimals that don't are those indeterminate decimals, like pi. Pi doesn't end. There's this formula that shows you why it doesn't end. Because if it does end, you could have a fraction. There's no fraction that represents pi. So the idea is that we had rationals. And then what we kind of merged into eventually was this concept of irrational numbers. This little secondary column over here where we had some irrationals. And we haven't really talked about those a lot. We'll eventually get into those. We'll start to see why this works. But irrational numbers, it's anything you cannot write as a fraction. So, non-repeating, non-terminating decimals. Yeah, we don't have a little symbol for it, but these are the symbols you'll see in college, and you'll get kind of used to them. Now, what we've been working with so far is everything we've been up till this point has been real numbers. Everything. There's maybe one section that we talked about where there was this idea that there was this possibility where we wouldn't get a real number. There was one section, it was in the beginning, it was in the prerequisites, so when we were talking about square roots, right, those are irrationals. They tend to be anyway. But there's this one category where they're imaginary. An imaginary number. An imaginary number, if you don't know, because obviously it's kind of like a made-up number, it doesn't actually exist. It's this idea, this concept in math, where there's this possibility where you'll get this idea of an imaginary number out of a math problem, and it actually comes up not from linear equations, but actual quadratics, curve of some sort, where at some point you're going to have in the middle of your problem a negative square root. So I'll go like a negative 1. This idea that when you're trying to take a square root, not a cube root or a fifth root, but an actual legitimate square root of a negative number, this does not exist. Does not exist, right? Because there's no way that you can figure out a number that would multiply on itself, its exact self anyway, that would give you the negative 1 in here. There's just no way, right? No, 1 times 1 is 1, negative 1 times negative 1 is positive 1 again. There's no way to get a negative on the inside, so it doesn't exist. Well, that's where they came up with the second category of numbers. It's not real numbers, right? It's this other complete separate list, which they call the complex numbers. So complex numbers. How that works, how a complex number works. You have a real number part, and you have an imaginary number part. And you put these two parts together. So the example I was using in the book is something like this. A plus B. I is italicized, and what this actually represents, that your A can be any real number you want, so let's say it's 7, and the B can be any number that you want, let's say 2, and you always have an I after it. What this little I stands for, I is this. This idea of the square root of a -1 is the imaginary number I.
Do you want us to write it out like that, or can we just write it
I. Great. So now I want to show you today like why we do this, how you're supposed to work with this. So that's kind of our goal, is go through some basic operations, show you kind of what the imaginary numbers are. Obviously you've seen them in Algebra 2. I'm hoping you have at least. Refresh your memory. It's been a long time since Algebra 2. You probably saw this maybe at the quarter of the way through Algebra 2. Yeah, third quarter-ish. That's about right. That's usually where they kind of introduce it. But a lot of people just, they see it, right? But you don't really know what it's for. You're told what it is, right? You're like, oh, it's a square root of a negative, but you never really see, like, where does it ever come from? And that's what I'm going to show you today. That's all I'm going to show you, like, where this comes from, why we're choosing this topic, why did I pick it after linear equations? Why is like this chapter follow chapter 1? It's kind of unique. But this is our concept today, right here. And I'm going to show you that. Make sense? So keep this in mind. This is our goal today, is to figure out why this works. What is this? Okay. But this was kind of a lead into it. This is where they eventually molded. Okay. So let's talk about this idea of imaginary numbers and where they would come into play and what that is, like what that little I is and how we use it. All right. So it's a Cartesian coordinate system, right? It's a graph, the rectangle coordinate plane, whatever you call it. And what we've done up till this point is linear equations. Something like y equals half x minus 3. Well, how do you graph that? Like, what form is this written in? Yeah, slope intercept, right? That's the form that we had on the board when we were taking that, the test. Slope intercept form. This is your intercept. This is the slope. The intercept we're actually dealing with here is the y-intercept. That's just how it always works. So that's where you hit the y-axis at -3, and the slope tells you to rise 1, run 2, rise 1, run 2, rise 1, run 2, and this is what the line looks like. It's a straight line. Okay? That's what we did in the last chapter. Well, what we're going to be doing in this chapter, chapter 2, is learning how to correctly draw curves. Any type of curve. Quadratic, cubic, any type. But I'm going to show you the shortcuts. Like this, that type of problem, that was a shortcut. Like how you start it, how you graph it. You can go over. The goal in this chapter is to show you to do curves, and that's where this is going to come into play. That stuff, this imaginary, because there's this idea that at some point there may be an imaginary number, and I'll explain the concept here. Okay. So, let me give you like a crash course in graphing curves. Here's my function, and this stands for y, if you want to know. And we have an x squared. Okay? So, these are the same thing. Well, what an x squared graph is, it's just a little curve. And it would hit 0, 0, it would hit 1, 1, hit -1, 1, because you square. Whatever number I plug in for x, you square it and you do the y. So -1 squared is 1. 2 is 4, -2 is 4, and you can kind of see they just kind of mimic each other. And so it is a curve, like that. Okay? And whatever you do to this problem, we can move it around, we can shorten it, we can widen it, we can drag it. Well, the idea here is how you actually, the easiest way to graph this thing is to look at the intercepts, the x and y intercepts, and then that tells you kind of where the curve is going. Okay? Because you need to realize anytime you have an x squared graph or curve, they're very symmetrical. The left and right side kind of mimic each other. They look almost identical. So there's this idea of what they call a line of symmetry that goes right down the middle of the picture. So imagine this is like a mirror. And when you look in the mirror, it's the same picture on the right and left side. Does that make sense? That's called an axis symmetry. Okay? So that's kind of the easiest way. Well, if you know where the intercepts are, where it hits the x-axis, where it hits the y-axis, you can draw it. Because the picture's going to look the same on the right and left side. They look almost identical to each other. Okay? As long as it's balanced on the equation, or on the y-axis. That type of thing. And you can move the axis symmetry wherever you want. Okay, so, going on that last problem. The easiest way to figure out where the intercepts are, the X-intercepts, is what you do is you factor this thing apart. Okay, you factor it apart. So, how do you break them in x squared evenly? What does x squared actually mean? Yeah, that's actually factoring it, right? Factoring is like breaking something up into things that multiply together. That's what the word factor actually defined as, right? And what you do is if you want to figure out where it hits the x-axis, that means the x-axis numbers, or the y-axis numbers, I should say, the y-axis number should be 0. Because if the y-axis numbers are 0, that's 0 on the y-axis, what this will tell you is where does this graph actually hit the x-axis at. So that's what you do, plug 0 in here. So, for this to be 0, one of these two things has to be 0. So what you do is you solve. You set this item equal to 0, you set this item equal to 0. And you solve. So if this is something more complex, you solve for x, and this tells you. So what is my answer for x that would make it hit 0? This. So the actual coordinate that would make the y number 0 would be x would be 0, right? And that would force the y to be 0. So the coordinate is actually 0, 0. So that's why it actually hits there on the graph. And that's actually the y-axis number as well. Now let's do this for a little more complex problem, right? And I'll explain the concept of where imaginary comes in, because it seems a little goofy, right? So let's do something a little more complex. So let's do a quadratic, still a quadratic because I'm going to have an x squared on it. X squared plus 3x plus 2. It's quadratic, has an x squared in it, so it's the same type of curve like we're looking here. A little bit different, but moved. Okay, that's all it is. So let's factor this apart. So how do I factor this then? Yeah, x plus 2, x plus 1. Right, that's how you factor it in two pieces from algebra class. And what you do is if you want to figure out like where this graph is going to hit the x-axis, because it's not going to look like this anymore, since they added some extra stuff on it, it's going to move it, that's all they're going to do. And what you do is you set 0 here, and you set each of these parentheses equal to 0. Because one of them has to be 0 for this thing to work out. So x plus 2 is equal to 0, x plus 1 is equal to 0, and you graph for this user, right? So solve, what would x be? 2 or -1, right? And so that's where it hit. It hit at -2 or -1, and this is basically what the graph looks like. And it's very symmetrical. So, the axis symmetry going down in the middle, so I knew kind of roughly where that point was going to be. And you can kind of draw a rough scale of this. And that's the idea. Well, so far, these all factor apart. They factor very nicely. So that means, I hit a very nice, easy, I hit a very easy x-axis numbers like this. I can hit y-axis numbers. So if you want to figure out where this thing actually hits instead of factoring to figure out where the x-intercepts are, to figure out where the y-intercepts are, now what you do is you plug 0 in here. So 0 squared, 3 times 0, plus 2. That will give you y-intercepts, because the x-axis number will be 0, right? So let's solve. What's 0 squared? Plus 0 plus 2. What is that number? 2. That's your y-intercept. So it will actually hit, I drew it a little bit off, I'll hit right here. So like that, and then that means, where this axis symmetry is, I'll hit, from this point, I'll hit, right about here. It's symmetrical, so so if this is the middle of the quadratic, I go 1/2 over, I go 1/2 over this way, and that's where it's symmetrical. That's how I can graph really quick. Well, the idea with imaginaries, why you ever get imaginary numbers, is because you won't have an x-intercept. It's the problem like this: y equals x squared plus 5x plus 7. right? It's this idea that numbers, there's like no way to factor that thing apart. So it's possible that I may not hit an x-axis. That's just something you need to realize. Okay, so the only way we can factor this type of problem apart, because obviously it doesn't factor in 2 parentheses, is the quadratic formula. So you put 0 in here, and I want to figure out where the x-axis is. So the quadratic formula, if you don't remember, is x equals negative b plus or minus square root b squared minus 4ac all over 2a, right? That's the formula that you learned back in Algebra 2. All this formula does, if you don't remember, it just gives you where is my graph x-axis. That's all it does for you. That's just what you need to realize. It's this idea of graphing, right? I know where my y-intercept is going to be. My y-intercept, if I plug zeros in for the x's, I'm going to hit positive 7. 1, 2, 3, 4, 5, 6, 7. I just know that by plugging zeros for the x's. But when I actually do this formula here, I get negative b, so negative 5, plus or minus square root 5 squared, because that's the b number, because again, this is a, this is b, this is c, right? And the a, b, and c are the actual digits. It's not the x's, it's just the numbers. So a is 1, b is 5, c is the 7. Right, I don't know why we've always used variables. So it's negative 5 plus or minus b squared, so that's 5 squared, minus 4 times a times c all over 2 times a, right? And what you're going to get, what you're going to notice here, is that we have negative 5 plus or minus, and then this is where it gets goofy, 25 minus 28 all over 2. What's the problem here? Yeah, you're going to have a negative number in the square root. That's an imaginary number. What this is telling you on this graph, it doesn't mean that the graph doesn't exist. It means that I'm never going to hit the x-axis. This graph has been shifted up. It's too high. It will never touch the x-axis. It's somewhere up here or over here, and the graph is curved up, but it never actually touched. That's when imaginary numbers come into play. It's hypothetically never going to touch it. It does not exist. Does that make sense now? Like what we use them for, where they come in? Now, eventually what we're going to learn in this chapter is how to graph that. Like, how do we draw that? Because obviously, I can't factor it. I can't pull it apart like this one. I know I can figure out the y-intercept, but I could not figure out where it's going to hit the x-axis at. So that's our goal throughout the entire chapter 2. Does that make sense now? What we're going to be learning? We're going to come back to that problem. That's a problem that we're going to try to eventually get to, maybe 2 or 3 sections in. Can we eventually graph that thing, like, very simple? Like, what's the strategies we have? Okay, but obviously now, right now, you're seeing for the first time this idea of where imaginary numbers come into play. The graph literally doesn't exist where it is the x-axis. That's the concept. Now, I'm going to show you complex numbers, what we're going to be doing here. Okay? So this idea of complex. So A plus BI. Right? So this idea of problems like this, how you get to something like this. And I'm going to show you for that problem over here. How we get to a complex number where there's a real part and there's an imaginary part. It's actually made from that thing right there. Okay, so x equals negative 5 plus or minus square root, what is that, negative 3? All over, what, 2? Okay, so how we get to this idea of imaginary numbers. When you have a square root where there's a negative sign on the inside like this, square root, not a cube root or anything like that, but a square root. What you do first is you separate the negative 3 to be like this. Negative 1 times square root of 3. That's the first step. That's the correct way to do it. Because the radicals can actually multiply together. So this would still be radical negative 3. Because when you multiply them, it stays in one radicals. So it's fully product rule for square root. Right? And when you pull the square root of negative 1 out, what did we say earlier? What was the square root of negative 1? It's imaginary number. It's I. Right? It's the imaginary number I. So this is what we have. We have negative 5 plus or minus I square root 3 all over 2. And how we get to this complex number. How we get to this complex number, like I showed you earlier, that A plus BI. What you do is, once we're to this point, you put the 2 under each item, and now you've separated them. So you have x negative 5 over 2 plus or minus I root 3 over 2. And this is the concept. It's A plus or minus some imaginary part. And the B number in this case, for this problem, is root 3 over 2. That's the number that's out front of the I, because you can put the I in the back. So this is how your problem works. That's the concept. My eye always looks like an F, so I try to. It's my italicized. Make sense now? Where these imaginary numbers come in and play this complex number. It's a completely different category of numbers. But this, I want to show you today, like, where it comes from, why we do it, why we chose to do this chapter. Because the last chapter, we didn't have any curves. There's only a few problems where we did where we substituted numbers and kind of plotted what it was doing. I'm going to try to show you throughout chapter 2 how to graph quadratics, cubic functions, how to do it really fast, shortcuts. What are things I look for when I graph things? How do I know what the picture will look like before I even start? Okay, questions, comments, or anything of the sort? My goal tomorrow, we're going to talk about some basic operations tomorrow on how to use, imaginary numbers, how you add them, how you subtract them, that kind of thing, how you multiply or divide them. And then show you kind of how we're going to do this for quadratics, what we're going to do for this. Okay? Make sense? All right, we're done for today. Very nice, very easy. We'll pick it up tomorrow. There's not a lot. It's just kind of an intro day where this topic is a very large overview of the entire chapter day. Don't feel like you're overwhelmed.
That sounds sick.
Okay, who needs to finish that test or start it? Okay. I'd like you to go to the back. We're going to have you sit back there, and we're going to have you try to time out at least a few problems. You've got about 15 minutes. Who else needs to take it? I have 2 for sure. Who's my third?
Jack, is Dyke one this week?
You were third. You said you're coming tomorrow?
What time?
That was 2 weeks ago.
This kid is a crap.
You need one 28 something.
What?
You need one like 28.
Yeah.
Okay, just a reminder to all the females in here, basketball practice starts today, so if any of you are interested in going out for girls basketball, you don't have to show up today, you can show up tomorrow if you've forgotten stuff. Or maybe you're interested.
She's the awesome 729. 38.
Oh, wait.
How's it going? I didn't hear it. I heard gone.
I'm really sick, Lord. No, like whole class.
What's wrong with this a bit? Alright, I just I had it like this, I had to like it over. And it's so straight up. No, I didn't get it. I just like what's wrong with it, just like it over.
Are you excited for basketball? You are?
That's cool. That's not even
How many girls?
No idea right now. There's some girls I know that they're in open gyms, but they didn't sign up. It's low number.
Sorry.
pretty good though.
Valley Mars.
Yeah.
Wait, when's the state football?
Hunter, are you gonna go down and watch?
Just make sure if you can.
When do they play?
I have no clue.
When are Chicago against Mississippi? Friday. Not this Friday. Next Friday.
Yeah, after 4 days of practice, I'm sure some of
We can go final.
We go.
No, just like I'm just better. That sucks. No, I'm doing no, how? It's like
Hey, no cell phones. Get rid of cell
12 to 4.
phones. Or wherever you need to.
And then you leave for like 2 hours, and then you come back and 6 to 9.
2 days in a row.
No big deal, just
Saturday, Sunday. I know. What? No, it's the week after.
Connor, is it your birthday today? Happy birthday.
Oh, happy birthday, Connor.
Jack, are we going to have Friday? I just like miss all school Friday. We see a lot of games. I don't know. I want to watch 2A.
You can watch Bishop Garrigan and St. Andrew. Who all would be in at 2A?
Union. Yeah,
Union, Boyden Hole.
November 12th. They play at 10.
Who does? 2A?
The 1A.
What about 2A? What's 2A?
Yeah, Bishop has Saturday. Saturday too. At 4 and 6.
Bishop Garrigan and St. Andrew won't even meet until the finals.
Right. Who's Bishop playing?
Well, my dad told me that if the boys won on Friday, they would have made the finals easy. Because that's how the practice. So, there's no reason that Bishop Garrigan should.
All the teams in Class A are 11 and 0.
Yeah, all 4 are.
And they're 1 through 4 ranked. They do play on the 11th. They play Friday. On day 1 and 10. Maybe we should go. Who is it? Boyd St. Ansgar plays Gladbrook.
Nick, you hear about Gary Mulder?
They've been playing West End Same semifinal.
Did you hear about our field trip on Thursday? We're going to Lucas basketball.
Or Jonas said maybe people.
Yeah, that's what he told me too.
I'm sure he'll tell him.
Yeah. Did he email us that? I didn't get anything about it. Actually good.
They'll probably do something. That's the logo instead of saying anything.
Oh, it doesn't say either. Are those boys basketball or?
Yeah. So they only have 2 games.
They are cool. Better than a running team.
What date's Friday? The 11th? 4 A games are after that. The 2 A games are 2 4 A games. This is number 4. Ink Centennial versus Dowling. And then Iowa City West versus Cedar Rapids, Washington. Yeah, it's like Valley. In Valley. I have Rapids Valley. Who's 30? Is it Denver?
Denver was A last year.
Denver's one. Those games would be good too, though. Denver versus Iowa. What's the game, man? They're 7.
Stewie, you look like a real mannequin. Stewie, you look like a real mannequin. I wish I had air. Where's the other one? One Danish got me as a car and I'm like, that week.
Scrimmage?
Yeah.
No, no, it's campus. Where are you going?
I'd be sitting there. Derek is in my wheelchair, holding up like a big bastard. And I was like this, I was like.
That's all it says, Jonah? That's all it is?
Yeah, he says nastier, but the shirt that says nastier needs to be earned.
Really?
That's like the cap. I know, because he should have earned.
Not bad.
Well,
Who?
I mean, at least they know what it's about here.
And he'd get up like halfway through and just walk out.
No, we're talking about a different map.
Jonah, I think I just scouted those 6 games because it said filter from 4 to 6.
Matt Holmes sees
The first game's like 4 to 6.
Never put two on that.
What?
Hey.
Yeah, I didn't know that. You were there for the minute, John. Due to elections.
I had to work. I was like,
No, I hate it. He never does it. Yo, Jack, what is that river battle bowl? River battle bowl that Jordan got into?
Like Iowa versus Nebraska.
What is that?
That's what it is. River Bowl. So it's kind of like any of those other ones, like Shrine and all those other games.
Who got in it?
Jordan Island, running backs.
Don't worry, he retweeted it.
There was some retweeted that he made too.
Bryce Flatter, Virginia Center, retweeted in. John Wayne,
So it's not that big a deal then?
It's when the vice president.
No, you like it so big. Like when they put that thing on Instagram. It's just like everyone.
He goes, Iowa versus Nebraska. It's like,
Only 3
three
teams
teams
in
Canada.
North Scott. What river is it? No. River is west of us. You know how he always puts stuff on Instagram. The most annoying thing is like the 3 people. He's like, only 2 teams recruiting me now. Sure, there's more to come. Don't sleep on me. Like, bro, I'm snoozing.
You know where he's
Bro,
going?
I'm
Ellsworth?
snoozing. What?
You're gonna
I
go
know
to
it's D-line and Josh Wayne.
I think he will.
No, I think
He's gonna go D3.
Wyland?
No, that's community, isn't it?
Yeah, I know.
Worst case scenarios.
Yeah, because JUCO's like,
Ellsworth is like a good one.
Ellsworth.
Ellsworth is a good JUCO too. It's not like 9 at JUCO.
Name like someone that goes to like college like this community college is like good.
Yeah.
You'd rather go like
Smart enough.
Yeah.
Or don't make a team.
There's Swagger one
Just
there,
like all-
and now he's at UAB. So he won.
Cam Newton.
Yeah.
You guys see the vote tomorrow?
What's his name? Brent Wagner went to
Is anyone 18 in here? Who's actually in vote?
But it's like,
I'm glad I got in this one.
You follow?
I'm very interested to see how tomorrow goes. I'm a little nervous.
I think he was just gonna be either go to the ball or
Please want me back. Practical vote, and I hope to God I get back in time. I have no idea how long I'll have to stay in line. When does the polling go by?
But when they're around against class,
Okay, I might have to go super early to some.
class 15. What even team is that?
Basketball, so it's like.
We're probably close like
Go
grand
go
teams.
back.
North Butler is actually playing their first game.
Not going to get on the
Not gonna-
They play teachers night here.
No, North Butler.
I don't want to.
What is that?
It's my first.
None of us here.
No one's gonna care, but.
I'm going to do this for a while.
Oh,
Miss May is
Very
right.
musical. She's like fired up about which is like,
Yeah, she gets so fired up. It's so fun.
But she was like director.
US president.
Don't like him. Don't like him.
That's funny.
I don't get how college
So
is.
I would never see her getting
I
like.
don't get how college is really sleeping. She gets
They probably just keep snoozing their alarm.
maybe because you're wearing like 170 pounds.
And it's the fire up about
The last I heard,
Probably not even
We're
the
really
second best running back in the year.
we're always.
Colton Francis.
Cole Francis is better.
More yards.
Okay, you said you're coming tomorrow morning?
He's so
I don't
lazy.
know what I'm
Seriously. Well, that's why his autism is rough.
At fullback, never goes to the middle, always bounces
That's like
everywhere.
this.
And on defense, he's like the worst DN. My dad's like, he's so long.
Well, that's why Jordan had on her title.
His name is next computer program, I think it's the same as last one.
Well, that's what Ryan, you don't
I was like, oh, I can use it. If I need it, yeah, because that's the one that's charged.
It goes on, it'll go on sale on Monday. Cyber Monday. I bought it for $29. Now it's summer sale.